Good afternoon. Welcome everybody to this session dedicated to health and safety. My name is José Luis Peña and I represent the Spanish Asphalt Producer Association, and on whose behalf I participate in the EAPA Health, Safety and Environment Committee. I would like to thank the organizer for giving me the opportunity to chair this session and to be able to interact with top technicians. During the next minutes, we are going to see 6 interesting presentations that offer valuable information for road users, enterprises, and public administrations involved in the asphalt paving sector. Health and safety issues are becoming increasingly important in the development of products and technologies and require a specific vision complementary with other technical aspects of the asphalt paving sector. I would like to remind the audience that questions can be submitted through the Slido tool, and we will try to answer as many as possible. Please specify whom is addressed each question as well as your name in order to identify properly each question. Presentation will be shown in 3 sections with 2 presentations each, after which there will be a Q&A session of approximately 7 minutes. The questions will not be answered through a Slido. I will select as many questions as possible and I will address them to the speakers during the Q&A section. Without further ado, I will now introduce our first speaker of the session, Nazan Ünal. She is a chemical engineer. She got her master and PhD degree from Gazi University in Ankara. She has been working at General Directorate as a road and building material engineer and work as a chief of laboratory training. She has been working as a chief of pavement management system for 17 years, and she's a member of the European Standardization Committee. Throughout her working career, she has been involved with the road sector focused on pavement materials, construction, and quality control. She is responsible for pavement management system, pavement performance, skid resistance, roughness, noise, rotting. She will show the presentation entitled Effect of Aggregate and Pavement Types on Skid Resistance Evolution. Emin, the floor is yours.
Okay. I'd like to present my regards. Effect of aggregates and pavement types on skid resistance evolution. Significance of the study. Skid resistance is an important indicator of road safety. Selection of the aggregates and pavement types are significant factors affecting the skid resistance. The result of this study had to choose the most suitable aggregates and pavement types. The aim of this work is to produce an inventory on skid resistance indicators of pavement across Turkey. The inventory is created taking into account different aggregates and pavement types. This information is used to predict friction change during the pavement lifetime, identify the appropriate time for maintenance, select maintenance alternative, proper materials and pavement types, allocation of maintenance resources. Skid resistance values were collected from different pavements with different aggregates. Measurements were started since the new construction of the pavements. The research covers micro and macro textures. The data were collected 2 different methods. Micro texture was measured by locked valve method using friction tester. Index is skid number, SN for short. Macro texture was measured laser method using profilometer. Index was mean profile depth, NPD for short. This study was conducted on 3 types of road and 8 different pavement sections. Road types are motorway, state highway, provincial road. These are under control of General Directorate of Highways. Pavement types are aggregates used in this study. Pavement types: stone mastic asphalt, dense graded wearing coarse, Portland cement concrete. Aggregates are basalts, limestones, granodiorite, and stream materials. Other materials are fly ash and boron. All basalts and limestones were different origin. Field results for wearing coarse and concrete. SN versus time. These are construction date. There are 4 sections on the plot. 3 of them were in coarse. 1 of them is in concrete. First were in coarse with basalt. Second were in coarse with 50% basalt, 50% limestone. Third with granodiorite. The last is concrete, including boron. All pavement ages were older than 11 years. Wearing coarse and concrete behaviors were similar. SN lower specification limit is 30 for Turkey. All SN values were quite good after 11 years. Results for SMA pavements. Their ages were between 3 and 6 years old. There are 4 SMA sections on the plot. 2 of them with basalt, 1 of them with basalt and fly ash, the other one with limestone. The SN curves behave differently. SN values increasing for 2 basalt sections, while the other were decreasing. SN increases as bitumen on the surface of the aggregate is worn away. Then it starts to decrease due to the polishing of exposed aggregate. Friction changes over time depending on aggregate type and mixture composition. Results for SN and NPD values for SMA pavements. SN and NPD versus time. There are 3 sections on the plot. Red is NPD, blue is SN. NPD values decreased. Macro texture is reduced and lost when the voids between the aggregates are filled with contaminates. For 2 basalt sections, SN and NPD curves were not similar. However, these curves show similarity for limestone SMA. Completion and recommendation. In this research, the main aim is to investigate the effect of aggregates and pavement types on skid resistance. It is need to choose the most suitable pavement types, aggregates, and to predict the skid resistance. The result of this study show that different aggregates and different effects on skid resistance even for the same pavement type. Pavements and aggregates should be evaluated together. The best results are obtained with basalt and granodiorite aggregates. However, under some conditions, the use of limestone is also recommended. Skid number evaluation for SMA. Their ages varied from 3 and 6 years. SN values of basalt SMAs were well conditioned. SN values of limestone SMA were higher than the lower limit. Limestone can be used in SMAs considering the skid resistance life. For wearing course, all SN values were good condition after 11 years. Pavements with basalt and granodiorite had better SN values than 50% basalt and 50% limestone mixture. However, It's recommended to use an aggregate mixture of 50% basalt and 50% limestone because its expected friction life is over 11 years. For concrete, SM values were well conditioned after 11 years. For other materials, boron in the concrete and fly ash in the SMA are thought to have a positive effect on skid resistance. NPD evaluation. Generally, all NPD values were low when we compared the two indexes. All NPD values decreased, while all SM values were found to be good and satisfactory on the same pavements and at the same periods. Thank you.
Thank you very much, Nazan, for the presentation about a very interesting topic, as clearly is related with the road safety. And let's go one moment. Here it is. Okay. Frank Bielefeld works for Extracton Civil as manager of the laboratory in the R&D department and the quality control department. He works on topics as intelligent compaction, information management, polymer modified bitumen, asphalt mixture and construction, and milieu impact of asphalt. In 2015, he finished his PhD degree in the University of Twente on the topic of professionalizing the asphalt construction product, aligning information technologies, operators, knowledge, and laboratory practices. He has published about his research in various journals, national and international conferences, and in professional magazines. He has given various presentations about this research for national and international press asphalt-related communities. During his research, he worked closely together with the 11 Dutch contractors within the Aspari project network that gives him a unique background and set of skills in asphalt road construction. So let's move on the presentation entitled "The Road Surface Label Used as a Functional Contracting to Stimulate Innovation," a case study on a motorway project in the Netherlands. Please, Frank, the floor is yours.
Hello everybody, my name is Frank Bielefeld and I work for Extracton Civil in the Netherlands. And today I will give a presentation about the road surface label used as functional contracting to stimulate innovation, a case study on a motorway project in the Netherlands. Also, I want to acknowledge my co-authors, Arjan de Bond from also Extracton Civil in Oostprodukten, and Harco Kesten from the province of Gelderland, who is now working for Rijkswaterstaat, the National Road Authority in the Netherlands. Shortly, the content of this presentation. I will explain something about the concept of the road surface label. I will explain the benefits for society. I will explain something about contracting and procurement of the pilot that we've conducted in the Netherlands with the road surface label. And I will explain something about the results of the motorway project. So why we have road surface labels, or why we need them. We believe that it's important recognition for society and politicians to make decisions between different road surfaces, similar as the tire label, or the label for houses, or the label for washing machines. And also we believe that it acknowledges that the road is the road surface as a product that can industrially be developed, designed, built, maintained, and removed. Also, it facilitates collaboration between tire manufacturers and road builders and other relevant partners like the automotive industry, leading to shorter innovation cycles. Also, it makes the optimization of tire-road interaction really possible. And finally, it facilitates interaction and communication with road users and residents. And we had the focus on developing a road surface label and not on changing or incorporating the tire label as well. So some benefits for society, and I've calculated some numbers for the Netherlands, but you can extrapolate the numbers for Europe and worldwide as well. So we believe labeling, road surface labeling, is a method to encourage progress and to stimulate optimization. And as you can see, the 4 items on the road surface label are skid resistance, noise reduction, rolling resistance, similar as the tire label. And we've decided to add also the lifespan as a parameter on the road surface label. And we believe that there is still a lot to gain on these parameters. So risk of accidents are 3 times smaller at a proper skid resistance. And in the Netherlands, the road accidents cost approximately 8 billion euros. So if we can improve the skid resistance, there is also a lot to save annually. Also, regarding the noise reduction, there is 9 dBA noise reduction that seems to be possible by optimizing the tire-road combination and tire-road interaction. This is based on results of a European project saving silent road traffic. Regarding rolling resistance, it seems that there is still 10 to 30% reduction of rolling resistance possible, and this means about 2 to 6% fuel savings. And only for the Netherlands, this means about 500,000 liters of fuel and about 1,000 kilotons of CO2. Also regarding the lifespan, it seems that there is longer lifespans possible. In the Netherlands, we normally use on the highway a 2-layer porous asphalt with a lifespan of about 9 years. But there are also innovations available. For example, an open porous asphalt that is widely used in Germany and also applied in the Netherlands with a lifespan of 12 to 14 years. Here's an example of the road surface label with the 4 individual items on the label. So noise reduction, wet skid resistance, rolling resistance, and lifespan. And here, this example is a DEEE label. And under the visualization of the road surface label, I've shown the label of various road surfaces. So you can see it varies from about B, C to G finally. We've decided to base the road surface label on existing measurement methods that are available in the Netherlands, in Europe, and some are also used worldwide. Here are some examples. So the CPX measurements for noise reduction, the rolling resistance trailer from the Technical University of Gdansk, the sideway forward measurement for the wet skid resistance, and we use HD cameras for inspection of the lifespan of the road in terms of raveling resistance, cracking resistance, rotting resistance, etc. Also, there are various methods available in the laboratory to determine the indicators of the road surface label. And here are some examples regarding noise reduction, rolling resistance, and on the left corner, you can see a machine that was applied in a European project SkidSafe to determine the skid resistance in the laboratory. Then the pilot that we've conducted in the Netherlands on the motorway A348, which is close to the border of Germany. And you can see the geography of the road. So the road was about 12.5 meters wide. And the stretch of the pilot was 2.3 kilometers. And you can see some pictures of the on-site construction process. Here's the table. You can see the procurement method that was applied. So it was a most economically advantageous tender in which 40% was determined by the price and 60% was determined by the quality. And the quality was determined by the road surface label. So a higher label indicator for each item on the label, you could score more quality. And more quality means that you had a fictive reduction on the price. And the contract was given based on the fictive price from various contractors. Here are some examples of the pilot of the motorway project. So we've constructed a 40 millimeter porous asphalt with 20% air voids. We've used a polymer modified bitumen with 5% SBS modification, Siloflex 590 porous asphalt. about 7% filler, 2.5% sand, and almost 85% of aggregate 4/8. And also we've added a binder drainage inhibitor. In the table, you can see the minimal requirements of the client. So in the first column, you can see that the minimal requirement of the client was an EDEE label. Then the next column, you can see what the contractor promised during the tender phase. So that was a DCBB label. Then there were some measurements conducted directly after construction. So what was realized in situ, you can see that the CBB label was realized directly after construction. And also there was a requirement after 15 years, a DCB label. Then some conclusions. So we believe that the road service label would be a step forwards towards professionalizing and industrializing the road construction industry. The described methodology in the road service label is a first step based on existing practical experience and the latest scientific knowledge. Enormous steps seem to be possible regarding skid resistance, noise reduction, eroding resistance, and lifespan. And we've demonstrated that it can be practically used in tenders for road services and to underpin that with existing measurement methods. Thank you very much for your attention. And if you want to ask any questions, you can contact me via this email address and phone number.
Thank you very much, Frank, for your very interesting presentation. I think that the labeling of the performance of roads, I think, is something that in the future will be quite common. So let's go for the Q&A session. I have several questions. Let me check. The first one is for Nathan. And Andre Taube asked, how influences the sand fraction the development of skid resistance?
Yes. I researched just aggregate type and pavement types on skid resistance. So unfortunately, I couldn't make a comment sand fraction.
Okay. The following question is anonymous. It's for Frank. And in theory, I think it's addressed to you, really. How are the optimization measured? The methods? That's the question. And there is also not really a question, but a comment addressed to you that says, it's from Jean-Claude Roffet, that says, excellent idea to label the road. What kind of benefit you got from road agencies? That's the comment and in some way a question. Sorry, Nathan. I thought you had finished your answer.
Yeah, I'm sorry. Sorry.
No, if you want to, please repeat your answer. If you want to, why?
No.
Okay.
Sorry.
Okay, Frank, the question was double in some way. How are the optimization measured? What type of methods you are using? And the following question and comment is from, as I said, from Jean-Claude Roffet, excellent idea to label the road. What kind of benefits you got from the road agencies?
Yeah, thank you for the question. I've explained something about the methods in the presentation, but in the paper we've explained in more detail the measurement methods. For example, regarding the skid resistance, we used the sideway force in situ measurement. And regarding the rolling resistance, for example, we used the trailer, in situ trailer of the Technical University of Gdansk. So we just use the existing measurement methods, both in the laboratory and in situ, and also, for example, some laboratory tests that we used for skid resistance in the lab was the friction after polishing, and also a machine that we've used for a European project named SkidSafe. And then the next question about the benefits for road agencies of the road service label. I think mainly it helps to make decisions between the different variables or different items on the service label. So, for example, you can choose for a road that has more noise reduction, but maybe not so long a lifespan. And also it helps an agency explain it to society and to politicians. So I think those are the main benefits for road agencies.
Okay, I have more questions and just a couple of minutes, 2-3 minutes more. I have a question for Nathan. It says, what type of mixtures are the so-called wearing courses in the presentation?
The wearing cores are dense graded hot mix asphalt pavement, which are placed on binder courses, and its thickness and their thickness are 5 centimeters, and they are for heavy traffic roads.
Okay.
Okay.
And I have more questions. In this case for Frank. Frank, from Matt, very interesting concept. Can you explain the potential of 10 to 30 rolling resistance reduction in a bit more detail? How might this be achieved?
Yeah, of course, the numbers are determined based on a study that was done in the Netherlands in 2014, where almost half of the Netherlands, or a third of the Netherlands, was measured by the Gdansk trailer, and we saw the differences in rolling resistance. So based on these numbers, we saw that there is a potential of 10 to 30%. And if you look into the literature, then there are 3 important parameters influencing the rolling resistance, which is the texture depth, of course, and then the longitudinal evenness of the roads and the stiffness of the whole construction. How exactly this is influenced by these 3 parameters is not exactly explained in the literature. So there is also still a role for universities and knowledge institutes to further explain and better measure the rolling resistance.
Okay, Frank, thank you very much. I think that we have 1 minute left for questions, and this one could be for Nathan. Which is in Turkey the specification for MPD in the case of SMA mixes?
Yes, we have 2 MPD values depending on maximum aggregate size. MPD index is equal and above 0.8 for 19 centimeters maximum aggregate size, and the other MPD value is specification value is 0.7 millimeters for 12.5 centimeter aggregate size.
Okay, thank you very much, Nathan. Thanks, Frank. Thank Nathan for this set of very interesting questions we have received from the audience. There are more questions. I just wanted to remind that there is a networking launch in the E&E Congress where you can address questions to all the people that is participating. So we don't have more time, perhaps a few minutes at the final of this session, but in case some questions cannot be addressed directly to the authors here, please use the networking launch. And please, Nathan, Frank, mute and switch off your cameras. We are going to go to the following block of this session, please.
Okay.
And let's continue the session introducing to Maria Elena Hidalgo. Maria Elena is civil engineer. She is a civil engineer and PhD in industrial engineering. She is technical manager in EFAS Infraestructuras with a wide experience in R&D projects management, most of them related with asphalt industry. She provides technical assistance to the production department in subjects such as asphalt mixes, quality, special mix design for a specific and new application, quality improvement in the laying of bituminous mixers, etc. She is also in charge of the coordination of innovation actions within the company. She represents EFAS Infraestructuras in technical forums, mainly in Spain, dissemination actions of EFAS know-how and technical support to customers. The following presentation, entitled Live Soundless Project Noise Reducing Asphalt Mixes with Recycled Materials, shows the result of obtaining the Live Soundless project, which has focused on the evaluation of the effectiveness of the Mediterranean climate of noise-reducing SMA mixes, incorporating rubber and plastic waste. Acoustic performance after 4 years of implementing the new pavement with SMA is keeping the difference from a new AC16 asphalt mix, the common surface layer asphalt in Andalusia. This acoustic performance has been tested throughout CPX and SPB methods. Environmental noise measurement campaigns were also carried out over 2 years, confirming the benefits of the soundless solution in terms of the acoustic behavior. Maria Elena, the floor is yours.
First of all, I'd like to thank the Technical Committee of the E&E Congress for selecting our paper for oral presentation. Now I'm going to highlight the main result obtained with the noise-reducing asphalt mixes developed during the Live Soundless project funded by the European Union. What were we aiming to achieve with this project? Well, we were looking to develop a pavement with good acoustic performance over time to be laid in southern regions with hot and dry weather. Due to the characteristic of the noisy urban areas where we wanted to act and the poor rainfall, the traditional porous asphalt proved ineffective over time, so we decided to explore other solutions. Also, we were very interested in using recycled materials as additive to the asphalt mixes. In this slide, we can see the main stages in the development of the project. First, we made an experimental initial diagnosis of the area through the analysis of noise maps and 3 on-site noise measurements. The first was rolling noise through the close proximity method. The second was the sound propagation close to the road through the statistical pass-by method. And the last were measurements of environmental noise over 24 hours. Regarding the asphalt mix design, we optimized the formulation to include recycled materials and validated this design in 2 pilot tracks carried out on 2 roads. Finally, we monitored the acoustic performance of the new asphalt over 4 years. There were 2 main aspects that we were considering when starting this project. The first was the acoustic performance, and the second was the environmental aspect of the pavement. Because we had previous experience using SMA mixes as noise-reducing pavements, we focused on optimizing the percentage of bitumen and waste materials to be incorporated into the mixture. The waste materials considered were plastic, rubber, and nylon fibers from end-life tires. We studied waste plastic from different sources: greenhouse plastic, master batches plastic, and wiring plastic. To select the most suitable composition of the stone mastic asphalt, we considered 2 criteria: the mechanical and the acoustic behavior. We tested 23 asphalt compositions. In this slide, you can see the results of the acoustic characterization through the testing of mechanical impedance. This can be measured by striking the road surface and recording the vibration of the material. We then analyze the response to obtain the dynamic stiffness, or Young modulus equivalent, and the damping factor, that is, the gap between the tire response and the force that excites it. The lower the modulus, the lower the wheel excitation, and therefore less noise generated. On the other hand, the higher the damping, the greater the delay and the lower the level of noise. This test was key to selecting the asphalt mixes we tested on the road. The best asphalt mixes in terms of acoustic results are those that have a low modulus and at the same time a high damping factor. Now we focus on the test sections. In the first scenario, with an average daily traffic of 30,000 vehicles and a speed limit of 50 km per hour, we tested the solution with a high bitumen content and rubber added directly to the mixer of the asphalt plant, what we call dry process. In the second scenario, 80,000 vehicles and a speed limit of 80 km per hour, we focus on the use of plastic waste in the mix, either plastic by itself or plastic mixed with rubber. Also, we tested the use of nylon fibers in the single lane on the service road and a reference section of asphalt concrete, which is the common asphalt mix that regional authorities in the south of Spain use on their conventional roads. Here we show the results of the mechanical performance of the asphalt. In both scenarios, the asphalt fulfilled the requirements of the Spanish specifications. Now we are going to focus on the acoustic performance over time. We start by presenting the results obtained in the measure of the rolling noise through the close proximity method at 50 km per hour. The starting point in time is February 2016, when the old pavement was evaluated. The gray line corresponds to the reference mix. This gray line. The lines in orange correspond to the asphalt with rubber, scenario 1, and the lines in green correspond to the asphalt with plastic, scenario 2. We observed that all the new pavements laid in May 2017 achieved a reduction of noise level, and this improvement decreased over time, which is logical. But we can also see that over the 4 years of testing, all soundless mixes maintain their noise reduction capacity with respect to a conventional asphalt concrete. More long-term testing needs to be done, but this is a very positive start. Also, we can conclude that the most noise-reducing asphalt has turned out to be the one containing 1.5% rubber. Here we see now the results from scenario 2 that show that the noise reduction capacity of soundless asphalt is also maintained at 80 km per hour. Now we focus on the evolution of the traffic noise levels to which citizens are subjected to. This can be estimated by the statistical pass-by method. The acoustic performance 2 years after laying the soundless pavement is quite good, remaining 3 decibels below noise levels before the project in scenario 1 and 8 decibels below in scenario 2. Finally, a sound measurement of global noise was done. The major attenuation regarding the initial situation was achieved in scenario 2, where we obtained a reduction of 6 decibels. Finally, I present the estimated impact on the exposed population after the implementation of soundless asphalt mixes and the consequent impact on the health cost of these people. I have no time here to explain in detail the basis for this calculation, so I refer you to our full paper. Here, I only want to point out that with the soundless asphalt mixes, we calculated that we could reduce by 70% the number of people exposed to noise level above the permitted Spanish regulation, and we could gain a 50% savings in health cost. Finally, I'm going to finish my presentation with our conclusions. First, the soundless mixes resulted in a noise reduction in the test areas. In urban areas with low speeds, such as scenario 1, the LDA was reduced by 3 decibels. In an intercity area with average speeds, such as scenario 2, the LDA was reduced by 6 decibels. Second, soundless mixes reduce road noise by 3 decibels compared to a new dense asphalt concrete at low speed and 4 decibels at average speeds. These values are similar to other studies in places with similar weather conditions. Third, the recycled materials used in soundless mixes have been shown to be effective in reducing rolling noise by stabilizing a higher bitumen content. And fourth, the reduction of affected population estimated by noise map models shows that the soundless mixes are effective solution for noise problem in urban areas. Thank you for your attention.
Thank you very much, Maria Elena, for your superb presentation, focusing on a quite interesting thing from my point of view, that is the noise reduction, but in the long term, checking that how a pavement behaves along the years. And let's go to the next presentation that will be shown by Lionel Green. He has been working in public road works for the past 20 years. Today, he is Technical and Innovation Director at Eurovia for the Paris area and Normandy. He is particularly involved in the various technical issues impacting our regional work sites, and in particular in the field of mastic asphalt and asphalt mix. Main concern today is to help develop new solutions in the light of environmental issues. Research shown in this paper intends to demonstrate how we can modify asphalt formulation to fight against two main urban disturbances: noise and excessive heat during hot weather conditions. Let's move to the presentation titled Cool and Low Noise Asphalt Live Project in Paris. Lionel, the floor is yours.
Good afternoon. It's a pleasure to be here today and to participate at the 7th Asphalt and Eurobitume Congress. During this virtual session, I will make a short presentation of Cool and Low Noise Asphalt Live project in Paris. As part of its environmental policy, the City of Paris has decided to include in the European Commission's LIFE program an ambitious project to develop urban bituminous surfaces to reduce two nuisances, which with the city is confronted. It is noise and it is excessive heat during heat waves. To this end, the City of Paris is assisted by Brit Paris, an independent non-profit organization, to assess and measure the noise. The companies Colas and Eurovia were approached in view of their capacity for study and innovation, their good knowledge of the Parisian context, and the opportunity of ongoing asphalt maintenance contracts with the city. The thermal aspect is managed by the public domain of Paris Laboratory and the Urban Ecology Agency, with a contribution of the Interdisciplinary Laboratory for the Energy of Tomorrow of the University of Paris Diderot. The team proposed the Cool Low Noise Asphalt project to the LIFE program. This program began on 1st July 2017 for a 5-year period. The project is estimated to cost 2.4 million euros and is supported by a 1.4 million euros grant from the European Commission's LIFE program. The City of Paris is very sensitive to environmental protection and is implementing a proactive policy to improve the living conditions of its inhabitants and combat the effects of global warming. These actions are carried out within the framework of Environmental Noise Prevention Plan and the Air, Climate and Energy Plan. The targets of the projects are the following. Concerning microclimatic effects, we can expect that world temperature drops by 2 degrees and that felt temperature drops by 3 degrees Celsius. Concerning phonic properties, we can expect -3 decibels at street level and -2 decibels on the other side. The main steps of the project that we will now quickly describe are the following. First, formulation of innovative materials, SMA Foam, BB Foam Plus, Puma. Then the choice of sites, sites instrumentation, the realization of the experimental test sections, monitoring of the experimental sections, and at last but not least, communication and dissemination. Firstly, I will make a focus on the formulation, and I will begin with compacted asphalt mixes. The reference was a type A thin asphalt concrete mix of 0-10 discontinuous granularity with a polymer modified binder. This is the reference in surface layer maintenance for the city of Paris. Its application thickness is 4 cm. The innovative products had to be usable instead of this product with the same thickness, durability, and low additional cost. The first option was to start with a stone mastic asphalt, SMA, 0-10 type surface coating, known for its high durability and improve its phonic properties by increasing the voids content and reducing the aggregate's size. The second option was to start from a very thin asphalt concrete, BBTM 06 formula, known for its low rolling noise emission, but characterized by poor resistance in urban environments, and improve its durability without penalizing excessively its sonic properties. The thermal aspect is achieved through the use of clear aggregates in this mixture and the preservation of a microtexture to ensure sufficient surface water retention during spraying operations. You can see on the slide the main characteristics of the two completed asphalt mixes. For these products, the key points are durability, voids, acoustic performance, modified binders, and color of aggregates. I will now talk about mastic asphalt. Historically, the city of Paris has always frequently used mastic asphalt technology for both sidewalk and street surfaces. Mastic asphalt must therefore meet the dual objectives of acoustic comfort and reducing the UHI effect. This product, the Puma, has been developed according to two principles. Combine the albedo properties of a light-colored aggregate with the porosity of lightweight aggregates. A surface treatment has to be carried out in order to remove the surface bituminous, mastic, and to highlight the light and porous aggregates. You can see on the slide the main characteristic of the Puma. For the Puma, key points are durability, clear aggregates, porous aggregates, and surface treatment. I would like now to make a focus on the site instrumentation, and the first point we refer to noise measurement. The means of measurement are illustrated on the slide. 6 permanent measuring stations have been installed to evaluate the acoustic performance of the innovative surface coatings and compare them with standard solutions. Digital audio recordings at the roadside and continuous CPX for close proximity noise measurements, consisting of measuring the noise emitted in the vicinity of a rolling test tower, completed the acoustic evaluation system. The second point of instrumentation will concern the thermal evaluation as illustrated on this slide. The thermal component of the project includes a monitoring of performance indicators based on an evaluation of the albedo effect and an evaluation of the watering effect of the innovating surface coatings. In order to better characterize the thermal behavior of innovative road surfaces, temperature and heat flow sensors were installed directly under the surface coatings. On this slide and on the following, you can see illustration of the experimental sites. Each pilot site has 2 sections of approximately 200 meters long, one with the traditional reference surface and the other with the innovative asphalt mix. you can see the application of the SMA phone on Rue Frémicourt, and you can see the BB phone Plus on Rue de Courcelles. On Rue Le Courbe, Puma, Experimental, and the AC2 reference mastic asphalts were applied on 2018 September. The innovative Puma was applied and shot blasted 1 month later to reveal the clear aggregates. On this slide and on the followings, you can see the first results. The project is the subject of an annual meeting at the Scientific Committee and a Stakeholders Committee, the last of which met on February 2021. The experimental sites will be monitored until 2022 and more if positive results. Today, I don't have enough time to figure out the different results, but concerning noise as well as microclimatic measurements, you can see the real effect of the innovative solutions in comparison with previous pavements or with the references. This first table presents the CPX measurements for the 3 pilot sites. This one presents the comparison of noise levels in facades, innovative pavements versus previous and control pavement. And at last, this one presents the microclimatic effect of watering. As a conclusion, I would say that the project shows that it is possible to reduce both traffic noise and temperature peaks using specific innovative asphalt pavement and watering. The monitoring of pilot sections will continue and provide long-term information in the next years.
Thank you, Lionel, for your interesting presentation about clearly topics that are in the agenda of, I think, that for most of the citizens. And now let's go to the following Q&A sessions. I have several questions. Let me check. The first one is for Elena, Maria Elena, and says, when you use plastics, how did you differentiate in terms of chemical composition? Plastic covers a wide range of products with different characteristics and also different potential impact. For example, on health, safety, and environmental aspect. How did you specify the consistency of material received and used?
Okay. Yes, he's right when she said that plastic, there are a very different type of plastic, but we only use, in the project, we only use low density polyethylene from the greenhouse crops that are very common in the south of Spain. Also wiring, plastic from wiring, for wiring cables, okay? For resort of the cover of the wiring. So these plastics are all low density polyethylene. And regarding the question about the consistency of material, well, the greenhouse plastic that we use, was obtained from a plant of recycled plastic. It was that plastic was the same source, the greenhouse, but it's true that if we want to use plastic in a large scale, we could have problem of consistency of material because we have to be confident in that the recycled plastics are giving us the low density polyethylene. Okay.
Thank you very much, Maria Elena. The following question, and is also linked to a comment, one is from Francois. He says, heat island effect is getting more and more important in large cities. We need to find solutions like the ones presented by Lionel with asphalt mixtures, that we have to find relevant solutions for our customers. And
it's for Lionel, no?
Yes, it's for Lionel. And the question is, it's anonymous, for how long will the project will be monitored?
Well, thank you for this. So it's for me.
Yes, it's for you, Lionel.
Okay. So thank you for this question. The project began in 2017, and will be followed during 5 years. And if results are positive, we will go on the following of the project.
Thank you, Lionel. I have another question for Elena. Why did you decide, it's anonymous this question, why did you decide to use an SMA with a high void content instead of a porous asphalt mixture as a reference mixture?
Yeah, well, when I say an SMA with high void content, in fact, there is not so high, okay? Because it's only about, we say high in comparing to the traditional SMA that is have about 4% maximum of void content, and this SMA used in the live project, in the Soundless project, were about 8% of void. For that reason, we say that are higher, okay? But and we don't use porous asphalt with more than 20% of void content, because in the south of Spain we have a very dry weather, and the previous experience showed that we had problem with filling the voids with dust and dirt. Okay, so they lose in a relatively short time the phonoacoustic performance. Okay, for that reason we wanted to check other mixes that at the beginning they don't obtain the benefit that a porous asphalt, but they last, the acoustic performance lasts more in our weather and in our situation. Weather condition lasts more than a porous asphalt. It was that reason.
Okay, thank you, Elena. The next question is for Lionel, and it comes from Bert Peters. Any idea why there is a big difference in sound absorption between BB phone plus 0 plus 0.6 equal to 0.75 and SMA phone 0.8 equal to 0.19?
It's a good question, very interesting question. Of course, there is a big difference of absorption between BB phone plus and SMA phone. So this it's not easy to give a good explanation, but I will try. The BB phone plus is an adaptation of the BBTM formula, and the formula of origin has already an absorption of 0.57%, whether SMA phone is linked to SMA, normal SMA, and the absorption is of 0.22. So there is at the origin a big difference between the both products, and it's the reason why there is this difference at the end with the two innovative products.
Okay. Next question for Marilena. Do you have test results for higher ratios of rubber up to 15% or plastic 5%, which might reflect more the reality?
Well, I think that I think that perhaps it's a misunderstanding, because we use 1% rubber and 1.5%, but in the mix, not comparing to the bitumen content. If we compare the quantity of rubber in terms of bitumen content, is 20%, 23, around 23% of rubber in the mix, not in the mix, in the bitumen. Okay, I think that when they are saying that up to 50%, I think that they are referring to rubber in the bitumen. And in our case, because we use the dry process, we add 1.5% of the total mix, or the total weight of the mix. So it represents about 23% of rubber in the bitumen. And in the plastic, 1.5 with a bitumen content of 5.8, I think. It represents around 17% of plastic in the bitumen. So I think there are high content of rubber and plastic if you refer to the bitumen content. Okay. I don't know if it's clear, but I think that is important to differentiate that we add the rubber and the plastic directly in the mixer, and this percentage are referred to the total weight of the mix, of the asphalt mix.
Okay, I think the time for this Q&A session is over. Perhaps there could be, we have some minutes at the final part of the session, and there is any question that it comes to former speakers. Perhaps we can address it. But anyway, thank you, Lionel. Thank you, Maria Elena, for your superb presentations. And I think the work you have presented in this session is really worthwhile. Thank you very much.
You're welcome.
Thank you.
So, and we have reached to the final stretch of this session, and the first presentation of this section corresponds to Anna Stenholm, Group Specialist in Toxicology in Nynäs, Sweden. After completing a Master of Toxicology from Karolinska Institute in Stockholm, Anna worked for a few years with Castro BP and Life Science before joining Nynäs in 2006. Sponsored by the Nynäs, she completed her PhD at Karolinska Institute in 2018 in respiratory toxicology. As company's specialist in toxicology, Anna supports sales and customers throughout Nynäs. Dr. Stenholm chairs the group of petroleum toxicologists in the EU trade organization CONCAWE that aim to enhance the knowledge of health hazards of petroleum products. Currently, she also chairs a joint EAPA Asphalt Institute Task Force working group on respiratory health and asphalt workers. The current study that she will present aims to increase the knowledge of particulate characteristics of asphalt fumes during paving using low-temperature asphalt is entitled Air Particle Measurements During Paving of Low-Temperature Asphalt. And Anna, the floor is yours.
Good afternoon. My name is Anna Stenholm. I work for Nynäs, and I'm going to present the air particle measurements during paving of low-temperature asphalt. And a bit of background. As you all know, the bitumen is a complex in its composition, and it contains very long hydrocarbons, predominantly longer than C25. And during paving at elevated temperature, bitumen emissions and asphalt emissions can form as gas, vapors, and aerosols. And generally, you measure the fumes in mass as total hydrocarbons, and you can't distinguish bitumen itself. So it's all the total hydrocarbons present in the air measured as milligram per cubic meter. And when you reduce the application temperature, you will also reduce the amount of asphalt fumes in the air. And this can be seen on this graph, where you have the exposure in milligram per cubic meter, depending on the different type of applications. Here comparing rolling of asphalt and mastic asphalt. And you can also see that the conventional asphalt in blue, the blue bars, are somewhat higher or a lot higher than using low temperature asphalt. And there is no real definition of low temperature asphalt, but generally it means that you pave, for instance, at 20 to 40 degrees lower than the equivalent conventional asphalt. That means about 100 to 140 degrees Celsius. And when you measure the amount of fumes in the air during paving, there's also a possibility to measure confounders, since, as I said, the hydrocarbon measured in the air can also pick up diesel exhaust from the equipment and road dust, and also additives, of course. But in this study, we are not so interested in the mass of the fumes, but rather the particles. Why the particles then? Particulate matter, or PM as they also called, is a known risk factor for adverse health effects. And the size is an important parameter here. The PM10 is a size fraction, and that means that the diameter of the particle is less than 10 micrometers. PM2.5 is less than 2.5 micrometers. And the ultrafine, they're really small, they're less than 100 nanometers in diameter. And you can see this on the picture to the right. The pink dots here is PM2.5. And this is in comparison to a human hair or the fine beach sand. And the small particles, they contribute very little to the total mass of the fume. Here instead, the number of particles is very important, so you count them. As I said, the asphalt fumes are generally reduced by lowering the application temperature. So now we wonder, would also the number of particles of different sizes be less with a lower application temperature using low temperature asphalt? So the objective of this study that we have performed is to increase the knowledge on the size, the number, and the concentration of the particulates in the asphalt fumes during paving with low temperature asphalt. So this is the method, what we wanted to do. We wanted to pave with low temperature asphalt at 140 degrees. We used KGO, which is an asphalt without any additives. We could measure over 2 days and 8 hours every day. We wanted to measure the amount and the size distribution of particles in the range between 15 and 5,000 nanometers. So quite a big range. And here we have the ideal conditions in the end of the paving season, with a road with hardly no traffic, very little wind, and no rain, as you can see. It's a very sunny day, with also very few confounders. And this is the setup. You have the paving train with the paver and the asphalt truck in front. In order to control the temperature of the paved asphalt, we have a heat camera on the end, on the top of the roof of the paver. And then behind the paver, you have a trolley with all the equipment. And behind the trolley, you have a generator to run the equipment on the trolley. And they are all with well distance behind, like 5 to 10 meters in between each other. On the trolley, you have all this, you have the equipment in order to measure the endpoints. You have the scanning mobility particle sizer together with an aerodynamic particle sizer and a PM10 inlet. So what were the results? If you look at the average particle concentration, the background when measuring was 1,500 particles per cubic centimeter. And during the paving with low temperature asphalt, it was 7,000 particles per cubic centimeters. Looking at the size, we looked in the range of 15 to 5,000 nanometers, and 80% of the particles in this range were ultrafine, meaning less than 100 nanometers. We managed to pave a few kilometers at 125 to 140 degrees Celsius. We had very few passing vehicles every hour, and when they passed, we deducted these particle measurements from the final results, not to have any extra confounder there. And we only used data which was twice as high as the background, which in the end was 70% of the data that was actually measured in the peak of the plume behind the paver. Unfortunately, in this study, we were not able to compare with 160 degrees conventional paving. That was not possible to do during this campaign. Instead, in order to compare with the results, there are a few comparable studies available in the literature. And first, focusing on the particle concentration. In the current study, we had 7,500 particles per cubic centimeter. Whereas if you compare that to the literature, there is a study looking at conventional paving at the highway, and that was 27,000 particles per cubic centimeters reported by Elin. And another study where they studied crumb rubber paving, and there they have quite higher numbers, to 20,000 to 140,000 particles per cubic centimeters in comparison, so quite a lot more. Looking at the mean particle diameter, we saw in the current study the mean was 55 nanometers, and we have about or more or less the same in the other two studies, seen at the highway and also paving with crumb rubber at higher temperatures. And just for comparison, the typical particle concentration in ambient urban air in Lund, which is a city in Sweden with 90,000 inhabitants, the background in such a city is 7,000 particles per cubic centimeters. So to the conclusions. This very first measuring campaign shows that low temperature asphalt paving caused low particle concentrations in the air, and these are comparable to a common particle concentration in just ambient urban air. And it generates considerably less particles than measured at higher temperatures during conventional paving in comparable studies. And with this, I would like to thank you, Karin, my colleague at Nynäs, and of course the personnel at Rice and Lund University, and a very big thank you to the paving team, of course, at Peab, who allowed us to measure during your work hours. Thank you very much.
Thank you very much, Anna. A super presentation as well, with a topic that I belong to the Health, Safety and Environment Committee of EAPA, and I promise this is really a very, very important topic for us. And let's go to the following presentation, the last of this section, and it will be presented by Logan Pogot. Logan is Market Development Manager at Creighton, based on the Netherlands, in charge of the technical development for polymer and pine chemical additives in paving and roofing application. He has a master's degree of civil engineering from École Nationale des Ponts et Chaussées, France. With 30 years of experience, he has capitalized a worldwide expertise on pavement engineering with pavement design, materials, job works, and research and development. He is representative for Creighton at EAPA and Eurobitume, chairman of the LCA Eurobitume LCA task force, and he will present today the evaluation of fume emissions from polymer modified bitumen as a work jointly made with Huelva University from Spain. His presentation is entitled Laboratory Evaluation of Emission from Polymer Modified Bitumen. Please, Logan, the floor is yours.
Muchas gracias, José Luis. Buenas tardes. Good afternoon, everyone. I will share with you today some results on laboratory evaluation of emission from polymer modified bitumen. While the previous presentation was on in situ measurement, for this experiment, we'll go back in the lab in close control environment. I would like to acknowledge my co-author for this specific paper, especially Emilio Morales from Universidad de Huelva, and my colleagues Erika Gelema and Donald Scott. While it's not my main domain of expertise, I've learned a lot over this study, and I will do my best to present in an easy way a complex matter. We all know that manufacturing asphalt mix at the mix plant requires elevated temperature during the production process and later application on the job site. Due to temperature, fume emissions are emitted. With constant focus on health and safety, there are more efforts to better know and assess fume emissions. At the same time, there are also constant demand for better roads, safe, reliable, and durable roads. The use of SBS in bitumen is now a well-established solution to enhance the performance and durability of asphalt pavement materials. However, with higher viscosity, it may require different mixing temperature during production and application of asphalt mix. How the use of PMBs in asphalt mix may affect fume emissions. There is not yet a harmonized protocol to assess fume emissions on either binder, asphalt mix, or in situ. Then, jointly with Huelva University, we looked at a novel and promising methodology in lab on binder scale to evaluate fume emissions. This methodology was applied to different PMBs. Let's go first through the experimental plan. All measurements were made on bitumen level. For this purpose, a neat bitumen 5070 was used as a reference bitumen, and two PMBs were included. The first one was a standard PMB 458060 using 3.5% FSBS D111. The second one was a highly modified bitumen with 7.5% of vinyl SBS polymer D243 using the same reference bitumen 5070 as a base bitumen. The test was run at 4 different temperatures, 140, 160, 180 as common possible mixing temperatures, and 200 degrees Celsius as an extreme case. All measurements were made in Duplo. The commonly gas chromatography and mass spectrometry was associated with initial thermal desorption, aiming at improving accuracy of measurement. More specifically, for the pH detection, an initial calibration of the methods was made with standard mixture containing the commonly recorded 16 pH foreseen in bitumen. First, here are some few physical properties. For the service temperature, at ambient temperature, the consistency, as recorded with penetration value, for the three binders were in the same range of order. While for the high temperature, the softening point temperature, the consistency for the PMB displayed higher values than the reference bitumen, with 10 degrees Celsius for the standard PMBs, up to 40 degrees Celsius for the highly modified one. Commonly, in fact, softening point temperature for this binder is about 85 degrees Celsius. Because of higher softening point for the PMBs, this binder displays higher viscosity at elevated temperature. However, the highly modified one did not increase significantly more as compared to the standard PMB. This is due to the choice of the SBS polymer having high vinyl content, which keeps the viscosity in a visible range, even a high concentration in the binder. For volatile organic compounds, the analysis was made directly with the GCM spectrum and recorded in 3 families: the alkanes, the monocycloparaffin, and the alkyl benzene. The total peak areas were used and considered as proportional to the quantity of emissions of the considered species. The results are presented in a relative way, knowing it was related to 3 grams of bitumen for a heat space volume of 0.02 liters. In average, it was observed that for every 20 degrees Celsius temperature increase, the total level of emissions was multiplied by 2. And in the case of PMB, as compared to the reference neat bitumen, there was relatively less emission. It may come from the fact that the base bitumen is already processed at elevated temperature during the production of the PMB, and thus may release already part of organic components. This may be also dependent on the base bitumen used. Polycyclic aromatic hydrocarbons were determined using an acquisition model performed in multiple reaction monitoring. First, the measurements were calibrated with a specific mixture of 16 pH to track. This initial step validates that the pH can be detected, and then the calibration of the signal of each pH with the known concentration. Again, the measurements were related to 3 grams of bitumen for 0.02 liter in space. The total pH emission was consistent with the VOC. The higher the temperature, the more recorded pH emissions. And for the PMB, somehow, lower levels than the reference bitumen. Again, it may depend on the base bitumen used. Qualitatively, the naphthalene was the highest contributor of the total detected pH, the blue bar here. Although surprisingly, very low level was observed for the standard PMBs. Overall, limited to no heavy pH were detected, which are often the bad boys. In conclusion, while PMB clearly brings some value to enhance the high temperature properties against rotting resistance, it may also require higher asphalt mixing temperature. Thus, the analysis of the emitted emissions is important to investigate. A new approach was used in this study with thermal desorption coupled with gas chromatography and mass spectrometry. The total record of VOC was observed to increase by a factor of 2 every 20 degrees Celsius, something which was already reported in literature. However, in the case of the PMB, at a given temperature, the level of VOC was lower than the reference bitumen. This may be a result of the production of the PMB before. In the pH analysis, the naphthalene is the predominant pH detected and no heavy pH detected. The same trends and VOC for the PMB has been observed, with, at a given temperature, less emission and at least no additional non-harmful compounds. Many thanks for your attention, and if you have any questions, I will be more than happy to answer, either at the end of the session or during the poster session.
Thank you very much, Logan. Please, I see you have joined to the virtual stage. And we have a long queue of questions. I think at this moment, most of them are addressed to Anna because people need some time to write down the questions. The first one, Anna, is from Christina Smith. And the question is, Anna, when you said that additives were co-founders, does that mean that they increase PM emissions? If so, what sort of additives do this? Which additives cause the most PM emissions?
Thank you, Christina, for that question. As I said, this was the first study monitoring what happens to the particles when we pave with low temperature asphalt. Generally, we do this normally with measuring the mass of the fume, just measuring total hydrocarbons. And we know from these measurements that additives and diesel exhausts and other types of confounders can be present when you measure. So we thought in this study, we tried to really minimize anything that could possibly be a confounder. If additives would be a true confounder in the end, we don't know that, but we wanted to exclude the possibility at least. And that could, of course, be a new study to see if additives truly would be a confounder or not, because at this moment in time, we don't know this. But now we just focused on the asphalt and the bitumes and as such.
Okay, thank you very much, Anna. I have the following question is also for you. Let me check where is it? From Ade Taube. Does water in the mix, for example, from RAP or from food bitumen, have an influence on the emission of particles?
Thanks, Andrea. Well, I wouldn't, again, at this stage, say that we know this already. This is something that we need to further investigate, the influence of water. It could well possibly influence the production of particles in the end.
Oh, thanks, Anna. The following question is for Logan. Let me check it. Is there any comparison with other smoke emission measurement methods, such as the one used by Ifstar in the laboratory or with on-site measurement methods?
It's a good question. So the experiment we did was on the binder at the lab scales, only on the binder. The experiment that was developed by Ifstar, Gustav Eiffel University, is on asphalt mix. So scaling to the mix protocol, but still in the lab. I think we can see, we did some joint measurement on the binder and afterwards on the mix. I think we can see the same trend, but result cannot be compared like with like, in the sense that the volume of the container is different. The concentration of bitumen is different. So it's quite hard to scale up from binder to mix and later, in fact, on the job site. On the job site is open scale. So the fumes and exhausts can go everywhere. Why, when you measure that in the lab, it's a closed container. So you concentrate all the emission and you just exhaust the fume for that. So the trends are similar, but the exact value are not comparable like with like.
Thanks, Logan, for the explanation. The following question is for Anna. It's from Guillaume Rosso, and it says, Anna, nice presentation. What's the difference in particle size between LTA and ambient, urban, air, inland?
Thank you for the question. Well, we don't know that at this stage, since we didn't look into the particle composition. And that would be something, again, that we could further investigate, because we don't truly know what type of chemical composition of the particles that we measured. So I can't tell you at this point in time exactly the difference in between Lund and the particles when we pave.
Okay, thank you, Anna. The next question is for Logan, and it is is the bitumen used for to produce the PMVs the same as that is included in the study?
Yeah, in fact, so we did measurement on a neat bitumen 5070, so common bitumen we can use on during paving application. This bitumen was used to make the HIMA, the highly modified bitumen. So we can compare the highly modified bitumen with the 5070. And for the other PMB, it was a different base bitumen. It may explain as well some difference in the results, where in fact this PMB was slightly lower in terms of emission. The base bitumen was a 70-100 with a different source of bitumen. So just to explain again that maybe everything is not set in the stone, having a look to the trends, definitively the emission increase the temperature. Maybe having processes the neat bitumen during the manufacturing of the PMB can already release some fumes. And then when we measure the fumes directly on the PMB, it's slightly lower than the neat bitumen. So we can compare the 50-70 with the highly modified, and the other PMB was using a different bitumen.
Okay, I have time for 2 questions more. The next one is also for you, Laurent. It comes from Carlos Lopez. In your presentation, the amount of VOC and PAH are greater in bitumen 50-70 than in PMV formulated with the same bitumen. What's the reason for that result? Do you think that during the production process of PMV, some of the VOC and PAH are released?
At the beginning, we were a bit surprised by some values. Really, it's a first experiment. There is no protocol, harmonized protocol to evaluate that. So one explanation indeed may be that when you manufacture PMB, you already heat the bitumen at 170, 180 degrees Celsius, and in a closed container. And maybe in this case, you already have some exhaust of fumes. And then you make the modification with SBS, and you store that, in fact, at a high temperature before to be used as a mixed plant. So it may be an explanation. We do not have exactly the right answer for that. And this is something we would like to further investigate in terms of processing.
Thank you, Laurent. And the last question, we are just on the limit of the session. It is for Anne. Let me, the Slido is moving and I lose the questions. So let me look. Here it is. It's anonymous, Anna, and the question is, why is measurement made 5 to 10 meters below the paver?
Yes, again, as I said in the presentation, one of the key factors that we wanted to eliminate when doing this study was to reduce the possible amount of confounders. And one confounder could be the exhaust from the equipment. So from the actual paver. So by having the measuring the analytical equipment about 10 meters behind, you will actually catch the fume from the paving activity rather than the fume from the paver, because that is something you're absolutely not interested in catching in your measurements. And the same with the generator, we had that well behind as well, because that was a petrol driven generator for the making electricity for the equipment. So you want that to be as far as away as possible as well to really get accurate numbers. So that's the reason.
Okay, thank you very much, Anna, for your answer. I think we have just on the limit, we cannot go on. Thank you very much for your answers and to the audience for the very interesting questions that they have raised. And just to finish the session, I would like that I'm sure that the audience has been very interested in many of the topics that we have that had been presented. If new questions arise, please, you can contact with the speakers through the networking lounge. I would like to thank to all the speakers and the audience for the work and interest shown that allowed us to see a very interesting presentation and having interaction with the audience. Thank you very much to all of you. We will see in the next E&E Congress. Okay, thank you very much.
Thank you. Bye.
Bye.